Okay, so let us talk about internal resistance. We are now at lesson 29. So you've probably heard me when we are talking about those circuits referring to V external. And I made a point to kind of emphasize on it because there is actually a difference between V external as well as V internal. And in this lesson, you're going to learn what that difference is. So, what is internal resistance? That should be our point of departure. What is internal resistance? So, internal resistance is the resistance which is present within a battery. So, every battery has what we call internal resistance, and we represent that with the letter R. So, that's internal resistance, and it is still measured in ohms. So in reality, all cells or batteries have an internal resistance, and internal resistors are always considered to be connected in series with the rest of the circuit. So now we have, let's draw a battery there. So this is how you normally identify if your circuit has an internal resistance or not. And then this would be the resistance, this would be the internal resistance with a value of R. And then normally they would draw these dotted lines, and this battery can now be connected to the rest of your circuit. So now we have to relate internal resistance to the rest of the circuit by defining what we call the EMF. So what is the EMF? An EMF of the battery, it's often described as the total energy supplied per coulomb of charge by the battery. What does that mean? That means actually, in simple terms, the way I want you to think about it is that in simple terms, EMF is that reading that you will get. So let me draw this quickly. Okay, I'm gonna just remove this. Let us say now you connected this so there's your battery with an internal resistance. It will also have something you call an EMF, and you'll see how it. And then let's say you connect this battery now to a voltmeter V, and you actually don't connect this thing to the rest of the circuit. Say we have R here, value R, a resistor with R, but it's not connected because we have a switch here S that is open. So there's no current flowing through the circuit at all because this switch is open. So meaning the battery is actually not connected to the external circuit. You will get a reading. You're gonna get a reading. Let's say you get a reading of 12,5. That reading that you get, that will be the EMF. So that will be the EMF of your battery. Now, all of a sudden, you decide to close this switch over here, and when you close it, so switch S is closed. When you close it, now you see that your voltmeter is going to give you a different value. So now it gives you what we call the external potential difference, and maybe that external potential would have dropped from 12.5 to maybe 12 volts. So now you must be noticing something. Where did the 0.5 volts go? And what is that? This 0.5 is what we actually call the internal potential difference of the battery. So you should always be careful in questions. Are you given the EMF, which is the total energy that is supplied by the battery per coulomb of charge? So that means that is the potential difference across this battery when it is not connected in a circuit like we've shown, like we've just demonstrated here. Or are you actually given the external voltage? So now to find out where did this 0.5 thing go, we can now define an equation and say the EMF is actually equals to V internal plus V external. So meaning V external, EMF, let me just write epsilon. So it's EMF, the symbol there is a Greek letter epsilon E, or it looks like a funny E, funny looking E, would actually be equals to minus V internal, which is equals to V external. So to find V external, we said that was 12.5, meaning the internal thingy, the internal potential difference was 0.5, which will give us our external, which we found to be 12 volts. So yeah, think about it in those terms. So now I've already defined this equation. It makes our job much easier because we can also write this as I So that's the current through the total current through our resistor multiplied by the internal resistance, the value for the internal resistor that we find in our battery, right? So this is just from Ohm's law. So where potential difference is just the product of current multiplied by resistance plus I, which is the total current in the circuit, multiplied by the total resistance in the circuit. In this case, the total resistance was R. But we can simplify it further. We say, okay, let's take out I, total current in the circuit, as a common factor between internal resistance as well as the total resistance in the circuit. So we have R plus R. So which is given as your EMF. Okay. So I'm hoping whatever I've just explained is making sense. So that EMF is the value that you would get on your voltmeter if the battery was not connected to the external circuit. V external is the value that you get on your voltmeter when this is actually a closed circuit, meaning there's current flowing in your circuit. In the first case, current is not flowing because the switch was open. Okay, so now let us reinforce what we have learned by taking a question. Okay, so consider the following diagram. So this is the diagram, the second diagram that is given to us, and it's a very interesting one. So we have a battery there with an EMF as well as an internal resistance. And then we have the total current over there flowing through it. And then obviously now here, this IT will be split into this branch. Let's call this branch I1, and then, or IS. IS, I'm very specific about why I'm saying IS, because if you look at these two resistors, they are connected in series with each other, even though they are, when the two of them are actually connected in parallel with R3. So I'll call this IS and I'll call this current over here I3 because this is the third resistor. And then if you close the circuit, then the current will just flow through our circuit and our circuit will be closed. Okay, let me read the question statement without getting ahead of myself. So when they say when this switch S is open, the reading on the voltmeter is 12V. So what is that 12V? Think about it in terms of what you've just explained. That 12V is actually our EMF, because it is the reading we get when there's actually no current flowing in our circuit because the switch is open. Correct. So when that switch is closed, they're saying an important thing. They're saying the current through resistor R2 is 1 ampere. So when we close this switch here, so now it's closed, we found that the resistor, so we said this is IS. So the current through this resistor, let's call that current I2, is 1 ampere. But what do we know about our resistors that are connected in series to each other? The current through them is the same. So the current through R1 and R2 will be the same, meaning the current at R1, which you call I1, will actually also be 1 ampere. And also, so IS, this current flowing through here, so remember that the total current will come and then it will split over here into IS and I3. So meaning the current IS is the same current that we find at R1 as well as the same current that we find at I2. So meaning our IS will actually be equals to 1 ampere. You'll see why it's important for me to mention these few things. Okay, so now they are asking us that calculate the total current of the circuit, and second question is saying calculate the internal resistance of the battery. So let us start. So to calculate the total current of the thing, I hope this is clear. Let me just try to adjust that. Okay, so to find the total current, you might say, okay, I can use Ohm's law, which says V external divided by R total. Do we know what IT is? No, that's what we're looking for. Do we know what V external is? No, we don't have this value. Do we know what RT is? Not really, but we can find it, right? Using those equations of resistance that we're familiar with. But now you realize we don't have two variables here, so we can't proceed in this way. A different way of proceeding would actually now to use the ratio. So how do we do that? The first step I would say, just reduce this two uh, resistors into one resistor, which we call RS. So RS, because they're connected in series, it means that the total of this of the total resistance for the serial connection would actually just be R1 plus R2, which is equals to 5 plus 3, which is equals to 8 ohms. Where am I going with this? Now that we have this, we can say, okay, let's find the ratio of the resistors that are connected in series to this resistor here at the bottom, which is we call R3. And we say that, so this one's is 8, the ratio will be 8 is to 4. Simplify, divide both sides, divide both parts by 2, so we have 4 divided by 4 will be 1, 8 divided by 4 will be 2. So the ratio of RS to R3 is nothing but 2 is to 1. Why is this important? If we found this, we can actually find the ratio of the current IS to the current that will flow here, which is I3. Remember, it's a ratio. We already know what IS is. We told you what it was when we were interpreting the circuit, and we said it's also 1 ampere. But because in terms of Ohm's law, they are inversely proportional, meaning if the ratio of the resistors is 2 is to 1, the ratio of the currents would actually be 1 is to 2. And now it's just a matter of cross multiplying. So when we say 1 multiplied by I3 will just be I3, which is equals to 2IS. So to find I3, I'm just mainly, so for every one part of IS, there's 2 parts of I3, right? So there we are. So 2, we said the value of IS, we found it to be 1. 2 times 1 is 2 times 1 is 2 amperes. But we were not asked to find I3. We were asked to find the total current. So the total current, remember that total current will actually be split into 2. So it will be made up of IS plus I3. So be this current here that flows in this branch, as well as this current that flows in the other branch. So IS, we know is that it's 1, plus we just found what I3 is, which is 2 amperes. So 1 plus 2 give us 3 amperes. So we found the total current in the, so IT is equals to 3 amperes in our circuit. Hope you could follow that logic. If you're struggling, you can always WhatsApp me. So the second question wanted us to calculate the internal resistance of the battery. So now we have to go back to our equation of EMF. So we have EMF equals to V internal plus V external. We've already discussed what each of these things are. And then this can be written as IR plus IR. So this is the total resistance in the external circuit, the resistance in the external circuit in the battery. Okay, and we can take this as a common factor and say R plus R, right? So we know what EMF is. We found it, it's 12. Was it 12 V? Yes. Do we know what this is? The total current? Yes, we know what that is. We found it to be 3 amperes. Do we know what this is? That's what we're looking for. Do we know what R is? The total resistance in the circuit. No, we don't know what it is, but we can definitely calculate it. So how would we then calculate it? So we already found out that RS is equals to, so if we combine these two resistors into one, we found that value to be 8 ohms. And then we have another R3. So RS is connected in parallel to R3, which is 4 ohm. And then to find the RP, we simply know it's going to be 1 over RS plus 1 over R3. So 1 over 8 plus 1 over 4. And if you do the maths, you find that 1 over RP is actually going to be 3 over 8. To make RP the subject, you simply invert this, and then RP is actually just going to be 8 over 3, which is a value of about 2.67 ohm. Okay, so now we have RP, which is this R over there, right? So we found R, we said it's 2.67. So meaning we can actually just find what R is. We can divide both sides by I, the current. So we find that E over I equals to R plus R. We want to be left with R on this side, so we can simply take this big R to the other side with E over I minus R equals to R. So we said 12 over total current is 3 minus 2,67, which will give us the value of our internal resistance. And if you put this in your calculator, you're going to find the value of about 1,33 ohm. So that's how you would normally go about answering a question involving internal resistance. So I hope that made sense. In the next lesson, I'm going to be looking at a question from a previous exam paper, and then we'll just wrap up our discussion on electric circuits, then move on to electrodynamics.